Okay, so we'll get started. I will also start sharing my screen. Okay, so right, so quantum mechanics was the big development in the 20th century, early part of 20th century, and we know that that almost all light that comes from atoms and molecules, a lot of it actually comes in lines and not in like some continuous spectrum, which is sort of unexpected from standard classical radiation arguments. Okay, so for example, if you have an electron going around a proton, like in Bohr's orbit, it should radiate continuously as its orbit shrinks. You should see higher and higher frequency radiation, but that's not what we see. What we see are discrete lines, and this was sort of the birth of quantum mechanics, right? The Bohr's model and so on. So spectroscopy and nature of electrons around atoms are very, very closely related. So we'll just sort of briefly touch upon various transitions that we can observe. So some common, okay, just a second, common atomic sort of molecular transitions. Okay, and we'll actually just do some order of magnitude estimates for these, right? So we all know Bohr's model, right? So we know Bohr's model for hydrogen atom, right? So you have a proton and then you have an electron going around an orbit, and what Bohr imagined was you just apply mv squared by a is the orbit, right, is equal to the force, which is z. Let me take a nucleus of charge z, so z e squared by a squared. So this is this force balance. The new thing that Bohr introduced was this. So this is Bohr's quantization condition, right? That the angular momentum of the electron around the proton cannot be any arbitrary value. It is quantized, and you only have specific orbits of electrons around a proton which satisfy this quantization condition. Okay, and if we combine these two, we get these various well-known formulae, such as A is equal to, you have these n orbits for which the radius is given by n squared h cross squared by me e squared by z, right? So this is, or n squared by z a naught, and a naught is the Bohr radius, which is 0.53 angstrom. Okay, so this everyone knows, right? So this is an. Similarly, we know that En, the energy of the nth level, is minus half mv squared. This is equal to minus z e squared by twice a, which is equal to minus z squared by n squared times 13.6 eV, or or this is also equal to minus z squared m e to the 4 by twice h cross squared, right? And this is the Rydberg. This is one Rydberg. So this is the, this is the energy of the n equal to 1 Bohr orbit of an electron around a proton. Okay. What about the velocity? So velocity in the nth orbit is equal to z e squared by n h cross, right? This is just this is so if you so there are two unknowns in these equations. One is a and one is v unknown. So you have two equations and two unknowns. So you solve for them. This is just Virial theorem also gives us this, that the total energy is half of the potential energy and it's equal to negative of the kinetic energy. So what is Vn? These are really for a particular level n. So basically, if I put 1 by a here, which is n squared, right? So this is correct, right? If I combine this and this, I get this. Right. So this is equal to z by n times e squared by h cross c times c. Right. So I've just divided and multiplied by c. So this is called the fine structure constant. So this is Sommerfeld's fine structure constant. And right, so basically what it means is that V by C for n equal to 1 electron is alpha, which is equal to 1 by 137, right? So, the electron, even in the innermost orbit, is non-relativistic, not moving close to C. So we can actually treat this problem non-relativistically. Right, and basically you have these orbits n equal to 1, right? So an goes like n squared. So the farther you go, n equal to 2, and n equal to 3, and so on. And you have these transitions, right? You can have an electron, say, going from here, transitioning to say n equal to 2, right? And it sort of releases a photon, h nu, and the energy of that photon, h nu, is equal to E3 minus E2, right? Which is equal to Rydberg times 1 by 2 squared minus 1 by 3 squared, right? This is all well known to everyone. So for example, 3 to 2. So, there are different series. So, if you have any question, you can please interrupt me and ask me. Okay. So there are different transitions. There are these different series, Lyman series, which goes, you have an excited state, which is high n. So this is to excited state to n equal to 1. So for example, Lyman series, right? So you have 2 to 1, 3 to 1, 4 to 1, and basically infinity to 1, right? So this is 2-to-1 transition is called Lyman alpha, and it has a wavelength of 1216 angstrom. So it falls in UV, and of course, and this is basically the ionization potential, right? And this corresponds to 912 angstrom, and an energy of 13.6 eV, right? Because you want to go from n equals 1 to n equals infinity, you require 13.6 eV, and the photon corresponding to that has 912 angstrom. It's useful to know these numbers. So this falls in here. These are all UV lines. Okay. Now then we have Balmer series. Balmer series lines fall in optical. This is n to n equal to 2. This is transition of electrons from higher n to n equal to 2. So for example, 3 to 2, 4 to 2. So these are called H alpha. This is called H alpha. So this is like Lyman. Ly stands for Lyman. H is what people use traditionally for Balmer series. So H alpha, H beta, H gamma, and so on. Okay, so this 3 to 2 is like 6536 angstrom or something like that. So this is an optical. These are all optical. These are optical. So these were the first lines observed in the hydrogen spectrum, because these fall in optical. And then we have from n equal to 3 and so on. Okay, but these are actually quite useful lines, these and these. N equal to 3, these are called Bastion lines, and after the people who discovered these, n equal to 4, you have bracket lines and so on. So basically spectroscopy was, these were all known before Balmer lines, and these specific transitions were known before Bohr's model was known. So this was like the motivation for this simple model that Bohr came up with. Any questions on this? I hope everyone knows this pretty well. This is like the foundational stuff. Okay. So these are the principal transitions, right? These are the principal transitions across different ends. But there are also something called fine structure, and fine structure has fine structure lines associated with them. Just like we have these principal lines, Lyman series, Balmer series, Bastion series, we have fine structure lines associated with other transitions. Can someone tell me about these fine structure lines if they know? Let me see. Oops.
Stark effect, or
no, this is not Stark effect. You have heard of LS coupling, spin orbit coupling. So this is splitting of this is not Stark effect. In Stark effect you have an external electric field which is imposed, and it sort of that's the perturbing Hamiltonian. Here splitting of, so this happens in absence of any external fields. It's not like Zeeman effect or Stark effect, right? So LS coupling you have heard of?
Yes, sir.
Yeah, levels. Where does it arrive? Why does it arise? Can someone say?
When the orbital angular momentum L and the spin angular momentum S are coupled to each other and then form the total angular momentum J, then the degeneracy due to the J means L plus half to L minus half. This
Okay, so this is this is like you can also think of it as coupling between electron magnetic moment, magnetic moment. Electron has a spin, and if you have a spinning charge, it has a magnetic moment. And B field due to nucleus in frame of moving electron. So basically, this is another way of, what you said is fine, but another way of looking at fine structure energy is basically you have a proton and you have an electron going around it, right? If you go to the frame of the electron, in electron's frame, right, this electric field, right, which is pulling this in, gets transformed into magnetic field, right? We remember this B prime is equal to gamma B minus V by C cross E. This is the transformation of transverse magnetic field. Okay, so if you go to electron rest frame, it's moving. So this electric field ZE squared by A due to the proton, if you go to the electron frame, right, so there is no magnetic field in the lab frame. So this, you can actually think of an electron's rest frame. You will have a magnetic field which is, and gamma is 1, electron velocity is 1 by 137 of C. So your magnetic field is V by C times the electric field, which is ZE by A, right, Q by R. So this is the electric field. So this is the magnetic field, and this is in the perpendicular. So this is the electric field, this is the direction of motion. So this magnetic field is perpendicular to the both. So it's phi hat, R hat. So it's in the direction of theta hat. Okay. This magnetic field is in the Z direction. Right. And this is the magnitude of this magnetic field. So, so you have this energy associated with this is equal to minus mu E dot B, right? So this is electron magnetic moment, right? Due to its own intrinsic spin. So electrons have a spin, which was sort of discovered, and they, even a free electron has a spin. And this is like a very fundamental property and can be understood from relativistic quantum mechanics. And now you have this this magnetic dipole is placed in the magnetic field due to this magnetic field. Okay, so this is the interaction energy. And so what is mu E? What is mu E? How do we calculate mu E? So you imagine an electron, being a macroscopic dipole, which is sort of a rotating dipole, or a charge which is rotating with some frequency. Okay, so we know that the magnetic dipole mu E is like BE times RE cubed, right? So if B is the magnetic field at the surface of this dipole, right? This is the relation between the magnetic moment and the magnetic field for a dipole, for a classical, for a macroscopic dipole, right? And mu is also equal to I times area, right? I is the current. So this is current of a loop. If you imagine it as a loop, this is the area of the loop. So right, so, and what is the size of an electron? Right, this electron spin. So this is like a classical model of electron spin, classical treatment. This is not quite right, but it gives you the right scalings. So RE is equal to E squared by ME C squared, right? This is, we have already encountered it when we discussed Thomson scattering. So this is the classical size of an electron. So in the classical model of an electron is spinning with some frequency, okay, and it has this size. So it corresponds to it has a magnetic moment because it's charge which is spinning. So there is current and it has some area. So let's see. And this is the relationship between the mu and magnetic field at the surface due to this dipole. So B due to this electron, spinning electron, times dl is equal to 4 pi by c times I. This is just Ampere's law, and this is equal to 4 pi by c times the charge of the electron divided by some spin time scale, right? The charge, the electron, this is the electron. This is the electron, and this is sort of spinning. So this is your B times 2 pi Re, the classical size of the electron is equal to this. But we also have Bohr's quantization, right, which says that angular momentum is quantized. So what does that say? So what is the angular momentum? So applied to angular momentum of spinning electron. What is that? So ME times RE squared times 2 pi by T spin. So this is like moment of inertia. So these are like, I'm not using like 2/5 ME RE squared. This is just scaling argument. And then this is I times omega is equal to NH cross or H cross. Right. So this is Bohr's quantization saying that you cannot have angular momentum smaller than H cross. No particle can have an angular momentum smaller than H cross. So this is Bohr's postulate. So what do we have? So now we have this equation and this equation, and we can just take the ratio so that this T spin drops out, and we get BE, B due to this electric field at the surface, B due to this electron at the surface of the electron, times 2 pi Re. I'm just taking the ratio divided by H cross is equal to 4 pi by C E by T spin ME RE squared. And there is a 2 pi here. So basically what it gives us is that, basically what it gives us, we know this equation also. So this gives us BE. So T spin go where there's, there's T spin. T spin gets cancelled. This is equal to 2E by ME RE squared C. Right, and mu is equal to BE by RE, BE times, sorry, not by, this magnetic moment of the electron. Okay, so I'm actually just giving a scaling, so BE times RE cube. This goes as E H cross by twice MEC. This is called Bohr Magneton. This is the unit of, magnetic moment associated with. So this is the unit of magnetic moment associated with spin or orbital angular momentum. So basically, there is a relationship between magnetic field and the spin, and this is what that is written in terms of H cross. Okay, so this is for an electron, right? If you have an electron, this is what you have for an electron, but you can also have a nucleus. You can have a nucleus, and if it has a spin, the same way you can have mu n is equal to E H cross by twice m nucleus mass times c. Right. So the same process, you have a spinning, like let's say a proton or a nucleus which has some charge, then this becomes proton's mass. So the spin for a proton, the magnetic moment for a proton is smaller than the magnetic moment for an electron because it's more massive. Okay, so let's estimate this energy. So what is this delta E? So delta E is mu E times B. Okay, and I'm just sort of taking absolute value just. So what do we have? So we have mu E is E H cross by twice MEC. And what is B? B is nothing but V by C, this expression, times Z E by A. Okay, A is the radius of that orbit. Now, we know this V by C, right? We know this V. V by C is nothing but Z times the fine structure constant, just this, right? I'm putting n equals 1. So V by C is just Z times alpha, the fine structure constant. And what is A for n equal to 1? Let's go back up a bit. Right. So this A is the radius. So this is equal to, I'm putting H equals 1. So this is H squared by Z ME E squared. So we have, so what you will get is, in fact, I'll get an alpha from here, and you can see actually there will be another alpha. So this is what I have. So sorry, this is A squared, not A. Right, the field is A squared. So this is A, so that, right, this because it's E by A squared. Field is A by A squared. Energy is E squared by A. So what do we get? So we have Z E squared by 2A, right? We know this. This is nothing but the energy of the orbit. Z E squared by 2A, and we have V by C, which is nothing but Z alpha times 1 by A. So 1 by A is H cross squared Z ME E squared. Right, 1 by A is here, and the remaining A is just that. And what do we have? We have twice MEC. We have H cross. Now this is just a Rydberg, right? So this is, so you know, the A is proportional to 1 by Z. So this becomes A0, and then there is a Z which comes up in the numerator. Right, this is A0 now. This is the Bohr radius. And now ZE squared by 2A0 is nothing but a Rydberg. Right, this is the energy of the n equal to 1 state. So what do we have? So M cancels. We have ZE squared. So this H cross cancels. So E squared by H cross C. We again get this, and this 2 factor went there. So we have 1 Rydberg times Z to the power of 4 alpha to the power of 2. E squared by HC is alpha. So this is the energy associated with LS, spin orbit coupling. The interaction between the electron's spin magnetic moment and the magnetic field that is experienced by it as it goes around the proton. So, you know, basically this gives us the energy scaling of fine structure lines, right? So, you know, these principal transitions, these principal levels are actually split further, because of this LS coupling. Okay, and this is called fine structure, and you can have like a transition between these levels, and that will give you, you know, that will give rise to these fine structure lines which are observed. Okay, and so this is the energy associated with the fine structure transitions. Okay, now let's calculate it. So if you have Z equal to 1, like a hydrogen atom, so delta E fine would be how much? So this is 13.6. Alpha square is like 10 to the minus 4, right? So this is like 1 MeV, small milli electron volt, because this is 10 to the minus 4 and 1 Rydberg is 13 eV. So fine structure transitions are of order 1 MeV, and the wavelength associated with them is 1 millimeter. How do we get that? Right. So, you know, 10 eV is like UV, and this is 10,000 times smaller than that. So 1000 angstrom times 10,000 is 1 millimeter. So 1000 angstrom is like 10 to the minus 6 meters, 10 to the minus 4. Right. So this is in millimeter. And if your Z equal to 5, for example, a higher ionization species, then this comes out. So this is 5 to the power of 4 alpha square. So this again comes out to be in 1 eV, which is like 5000 angstrom, again in optical. Okay, so are you getting this point? Hello. So this is about fine structure. So some of the examples are examples of popular fine structure lines in astrophysics are oxygen 3 and oxygen 1 and carbon 2. Right, so basically oxygen 3 means that 2 electrons have been stripped from neutral oxygen. So this is oxygen from where we have removed 2 electrons. So this is oxygen 2 plus. This is oxygen 1. So this is neutral oxygen. So neutral. This is carbon plus. and this brackets means these are forbidden transitions. Basically, their probability is very, very small. Their cross sections are very small, but they occur because in sort of, occur in dilute medium in astrophysics. Therefore they are common in astrophysics because astrophysical gases are very dilute. So this is 4.364 angstrom. So this again, see, as I said, this has Z of 2, right? So 2 to the power of 4, and no, sorry. So this is Z of oxygen, right? So oxygen has a has a nucleus with a charge of 6, right? So 2, sorry. So oxygen has 8 protons. So Z, right? But there are also 2 so this is oxygen 2+, and if you're looking at the outer electrons, then some of these protons are shielded. So for complex atoms, it's difficult to just apply this scaling right away. But for example, oxygen 1, this is 63 microns. So this has a longer wavelength than that because Z is smaller, because most of the protons, most of the nucleus's charge is balanced by the inner electrons. So this is carbon 2, this is 158 microns. This is a very important line for cooling of the neutral interstellar medium, which is at sort of 100 Kelvin or smaller. Similarly, these are also very important coolants of this temperature gas. Okay. So this is about fine structure. Let's see. Any question? Right, so I'm actually giving a very quick introduction to this subject, but you must have done this fine structure and LS coupling and so on in some course previously. Here I'm actually giving you more physical and classical treatment. Okay, but this is actually quite nice. What's most important is this scaling. Right? This sets the energy scale of these fine structure splittings. So this is alpha square, Z to the 4. Right? If you have a single electron around a high Z nucleus, then you can apply this precisely. But even when you have multi-electron systems, getting this from just that scaling is difficult. But you can actually see that the energy scale is smaller compared to the principal transitions of hydrogen, for example. Okay, what else? So there is something called hyperfine splitting or hyperfine levels. So can someone tell me about the hyperfine levels, hyperfine transitions?
Is the 1.4
Yes,
gigahertz one?
Yes, that's the 21 centimeter. But
Yeah,
why
21
is it nice? What is like the energy coupling in this?
It's like
coupling
the
between
proton
nuclear
spin and the
spin and
electron spin.
electron orbital angular momentum.
Right. So one by one, actually. So this is the interaction of electron spin, basically dipole, the magnetic dipole associated with the electron and proton or nuclear spin. So you have a proton or a nucleus which has a spin associated with it, and you have an electron which is going around it, which has a spin associated with it. So if you have, this proton, spinning proton, will create magnetic field at the location of the electron, right? So it's sort of like, if you have two dipoles, right? They, the magnetic field due to this dipole here will cause an energy to be associated, right? The interaction energy of the two dipoles. Okay, let's try to estimate this. So yeah, the famous 21 centimeter line is an example of hyperfine splitting, hyperfine transition. Okay, let's do this. Right, so the energy is basically mu dot b, right? Mu dot b, mu of electronic spin, that mu b due to proton at the location of electron. Okay, so what is b? This is mu of the proton divided by r cube, a cube, because let's assume hydrogen only. So this is a proton, and you have an electron, and this is the orbit radius. So this is bp is just mu p by a cube times mu e, right? Recall delta E fine structure. What was this? This is equal to mu E times V by C times E by A, right? So E by A squared. This is the electric field. This is the electric field, and V by C times the electric field is the magnetic field, and mu E. So this is mu E dot B due to fine structure interaction. Now here we have mu E and we have this. You recall, just like we can spin associate an electron spin, there is a proton or a nuclear spin which is just simply given by this, right? So so mu P is nothing but E h cross by twice MP C, right? That's the value of spin in terms of atomic constants, h cross and mass and so on, times mu E by A square times 1 by A. I'm actually writing it in this form because I can use this mu E by A squared, right? So I mean, we have the same thing here, mu E by A squared. So I want to actually compare this, the fine structure, hyperfine line with the fine structure line. Okay, so mu E is there, A square is there, 1 by A. And what is 1 by A? A is just h cross squared by z me squared. Okay, let me just write that down. Right, so this is equal to, so 1 by A is what? Let me just write this down. 1 by A is ZME E squared by h cross squared. Okay, so what do I have? I have, basically this is nothing but me by mp times delta E fine structure, right? So basically the hyperfine, so delta E hyperfine is about a factor of 2000, the ratio of electron to proton, smaller than the fine structure splitting. Do I get that? Let's see. So this is nothing but ZE by A squared. I have a V by C there. Let's see. What is V by C? V by C is nothing but alpha. This is V by C is nothing but alpha times Z. So E squared by H cross C. So this is E squared by H cross C. This is nothing but alpha. Right, so everything else is there. Z is there, alpha is there, mu E is there. The only thing that remains is 1 by MP. So this is the scaling, okay? So what does it give us? So it gives us that delta, this is of order ME by MP times Z to the 4 alpha square, right? So how much does it come out to be? So if you put Z equal to 1, that is hydrogen atom, you get it to be delta E hyperfine is, so 10 to the minus 4 times 1 by 2000. So this is about 1 micro electron volt. And if you convert it into lambda, lambda is equal to E by, sorry, just a sec. So we can actually easily convert energy into wavelength, right? We know that E equals PC and is equal to HC by lambda. So lambda equals HC by E. If we plug in the numbers, we get lambda for this is about 100 centimeter, right? And we know that lambda of H1, this famous hyperfine line, is 21 centimeter. Okay, so this is just a way to get these scalings. Okay, and these, you have all done very rigorous courses on LS coupling and whatnot, but these are very simple but very physically robust estimates of the scaling of various energy splittings because of spin-orbit coupling or the spin-spin coupling between the proton and the electron. Yeah, I like this derivation quite a bit because it gives us the overall scalings of these things and some intuition. Okay, so these are these are for atoms, but there are also molecular transitions, right? And the trick for all this is to actually have a Hamiltonian, calculate eigenfunctions and eigenvalues and so on, right? So you can have molecular transitions corresponds to vibrations, vibrational and rotations. So for example, if you have say H2 molecule, you can have this vibrational motion like a like a spring a mass attached to a spring, right? So these are vibrational interactions between particles, right? And it can actually be treated as a harmonic oscillator. Or you can have, you can have CO or CO2 or, CO molecule, carbon monoxide. Very important coolant, coolant for 10 Kelvin molecular gas in ISM. Okay, so this can have rotational and vibrational transitions. The energy scale is much smaller. Let's see. Right, for a harmonic oscillator, we know that for a quantum harmonic oscillator, energy is n plus a half times h cross omega. And omega, we can actually estimate, is just, classically actually k by amp. Right, so this k is the, Hooke's law, right? For a spring, right, F equals minus kx. X is the displacement, so that's that k. And amp is the mass of the nucleus. Right here, nuclei are sort of vibrating. And actually, we can estimate these things as well. What is the energy scale of these transitions? For example, this is for vibrational transitions, right? For rotation, we actually take I, this is the moment of inertia of the molecule. Depending on the orientation of its rotation, we take Hamiltonian as I omega is half I omega squared. Right. So similarly here we have, so this is the kinetic energy. Here we have potential energy, which is half kx squared. This is the mass of the nucleus. Right. So how do we estimate this k for these molecules vibrating? So k a naught. A naught is the size of displacement. A naught is the size, these the separation of atoms in a molecule is of order the Bohr radius. That sets the scale actually for separation between atoms in a molecule. So we have Ka naught, which is of order E squared by A naught squared. I'm just sort of equating the electrostatic attraction with the Hooke's law, spring force. So this gives us K, and omega naught associated with that is just E squared by A naught cube AMP. Right, so if we plug in the numbers, we get that En for the nth level, this guy, just scales as Rydberg, right? The principal energy associated with n equal to 1 orbit times me by amp to the 1/2. Right, so this is the scaling. You just plug in A0 and this is what you get. A0 and Rydberg. If you plug in, you will get this energy scale for vibrational transitions of molecules. So let's see. So for example, H2, right? For H2 molecule, we have, what is the energy scale? Me by mp square root of that. A is 1 because it's H2. Hydrogen has just one proton, so this is about 1 Rydberg by 42. Square root of 2000, is 40. Sorry, this is Me by mp is 1 by 2000, and square root of that is about this much, right? 42 squared is 1800. So which is about 0.3 eV. 13.6 divided by 42. So this is near infrared. So you do see H2 absorption and emission in near infrared. Similarly, what about SiO? SiO is a heavier molecule. So its A is bigger, of order 20. This A, this one, this A. Nuclear mass is bigger. So this is about 0.05 eV, which appears in mid-infrared. So this is how actually one can get a sense of which energy, what sort of transitions, what sort of interactions fall in what sort of bands, wave bands. Okay, so this is just about the transitions, but there is much more. There are terms like selection rules, like dipole transitions, selection rules. For example, dipole, quadrupole, and so on. And there are things like calculation of transition probabilities. Like Einstein's A and B coefficients. This is the whole sort of purview of atomic physics, right? They calculate these energy levels and tell us the selection rules and the strength of Einstein's A's and B coefficients and so on. Okay, but we are actually not going to do that in detail, but you have to have some idea of that there are certain selection rules. Certain transitions have very high probability of occurring, right? For example, n equals 2 to 1 Lyman alpha transition, right? And certain transitions like these forbidden transitions, like this 21 centimeter transition, are forbidden transitions, so they have low probability. So the cross section and oscillator strengths associated with them are smaller. So one has to actually have some idea about all this. Okay, so this is about, this is just a whirlwind introduction to various transitions that give rise to important observational lines. Okay, so now I will actually come to, once you have a line, right? So basically to form a line, you need these discrete energy levels, and these discrete energy levels can arise because of various interactions that we talked about, like fine structure interaction, or hyperfine interaction, or just the electrostatic interaction in an atom, or vibrational interactions of molecules within a molecule of atoms, or rotation of molecules. So all these have, in quantum mechanics, all these processes, all these Hamiltonians have discrete energy levels associated with them. And when the system transitions from a higher energy to a lower energy state, there is a photon that can actually be emitted, right? Provided these selection rules are satisfied. And these photons are emitted in form of lines, right? They are very discrete, definite frequencies associated with these transitions. Okay, so this is how lines are produced in the first place. Now we are actually going to talk about line broadening mechanisms. What happens once you have a line? What after that? Okay, so now we'll talk about line broadening mechanisms. So how do discrete line transitions broaden due to various physical processes? Okay, so we are actually going to cover a few of these processes. Let's see. Right, so you have these two discrete levels, say 1 and 2. These can actually be like n equals 1 to 2 energy levels of hydrogen. These can be fine structure, fine structure energy levels, or hyperfine energy levels, or whatever, or molecular levels, or rotational levels, vibrational levels. This is like a generic feature of quantum mechanics, that you have discrete energy levels. Okay, so if you have dx, if your electron goes from 2 to 1, there is a photon which is released. Now, these levels are not infinitely sharp, right? They have finite width of energy. Okay, and it's sort of governed by energy, time, uncertainty. So, if delta E, delta T is H cross. Now, this delta E is the energy uncertainty in the energy of level. Okay, and delta T is sort of the lifetime of an electron in that level. So this can also be thought of as, delta omega tau of order 1, right? So like in Fourier space. So the width, so if you have like a pulse, right, it has some tau, the times, the width in time of this signal, right? And delta omega is so this is time, this is frequency. If you do a Fourier transform of this, it will have some peak at omega naught, which corresponds to this time scale, and it has a width delta omega, which is of order 1 by tau. Okay, so this is actually related to this Fourier description of a signal in time and a signal in frequency. So so these energy levels are not like perfectly constant energy. They have some width associated with them. So that would mean that the photon that comes out is not a delta function in frequency. It has some width associated with it, which we can call like a line profile, right? Which is characterized by a line profile. Okay. Right, and because of this finite lifetime of these levels, what happens is you have some so we can actually introduce this decay of state n right? So we can actually have a decay constant gamma, which is equal to n prime a n prime. So some electron in some state n can actually decay to various states n prime which are below it. So this is like this is sort of like spontaneous emission or decay. So right, so because of this decay, there is like e to the minus gamma t decay in the intensity. Right, if you recall, we did this harmonic oscillator model for an electron, right? Where we considered an electron. We considered a bound electron with some natural frequency and some radiation damping, if you recall, right? We considered an electron which is undergoing dipole radiation, but since the electron is radiating, there is this radiation force, the classical radiation force, which is proportional to x triple dot, and that gives rise to the damping of the motion of this dipole. Okay, so there is this gamma factor associated with that. Right, recall F was proportional to x triple dot, radiation damping. So same language actually can be used for decay of electrons from one energy level to another. Okay, and it gives rise to a Lorenzian profile, right, which we actually derived, right? We had this oscillator equation x double dot plus gamma x dot plus omega dot squared x equal to 0, and this was due to the damping term, due to this radiation reaction force. It was actually x triple dot, but we can actually, in the limit where omega naught is much bigger than gamma, we can write it as x dot term. Okay. So this, when we solve for x for this, it gives rise to this line profile phi nu is equal to gamma by 4 pi squared divided by nu minus nu naught whole square plus gamma by 4 pi squared, right? So this is the normalized Lorenzian line profile. And this gamma is related to this decay and this finite lifetime, right? So because of this gamma decay, the state has a finite lifetime, which is 1 over gamma. So if gamma is infinity, you can have a very long, if gamma is very large, you can have a very long lifetime. That is, this tau is very, very big, or delta omega is very, very small. It's a very, very neat, very narrow frequency signal. Right, and this gamma is actually related to the broadening of both the low and the high states, right? This transition will have uncertainty because of the uncertainty of the higher state and the low state. So this is a Lorenzian profile. We have actually dealt with it so phi nu as a function of nu. How does it look like? It sort of peaks at nu equal to nu naught. And it sort of has these. It has these wings which fall off like 1 over nu squared, far away from nu naught. They are not exponentially decaying. They have these are Lorenzian wings, which fall off at high frequencies as 1 by nu minus nu naught squared, right? It does not as e to the minus nu naught squared by sigma squared, right? They do not fall very fast. So these are called the wings. Okay. So this is and this is called natural broadening. This is a fundamental. You cannot avoid this. This is a consequence of uncertainty principle, that you cannot have energy which is absolutely precise. There is some uncertainty associated with energy, and that causes this finite lifetime of the energy level. Okay, so this is natural broadening, and it gives rise to a Lorenzian profile, line profile. Okay, what else? There is something called, so this is first broadening mechanism. There is something called Doppler broadening. So what happens in Doppler broadening, that so if you have particles with some temperature have a distribution of velocities, right? So the observed line will be broadened because some particles are coming towards you and some are moving away from you, and so on, right? So a line, for example, this electron or this atom will emit a line which would be blue shifted, and this electron will emit a line which would be red shifted because it's moving away from the observer. So even a narrow line, because of this random motion of electrons, can become broader. Okay, how does it work? Let's see. So let's assume V by C is much less than 1. So particles are non-relativistic. Okay, so we know that nu minus nu naught is equal to nu naught Vz by C. So let's consider this to be the z-axis, right? So the observed frequency, and this is the rest frame. Electron, the atom's rest frame frequency, which is like, for example, 1216 angstrom of Lyman alpha. So this is the physics in the rest frame of this atom. But because of this motion, the observed frequency is slightly higher or lower because Vz is either positive or negative. Okay, so Vz is the line of sight velocity. So Vz greater than 0, your observed frequency is higher, so it's a blue shift. So we know that dn is proportional to exponential of minus mvz squared by twice kt dvz. Right? This is the Maxwell-Boltzmann distribution of velocities. Now we want to, right, so this is nu and Vz have a one-to-one relationship between velocity Vz and nu. So we can actually do a rate, we can actually change the variable from Vz to nu. Okay, so we have Vz equals C nu minus nu naught divided by nu naught, and dVz equals C d nu by nu naught. Okay, so the strength of line is actually proportional to dn, is proportional to exp. So I'm doing a change of variable now, minus m by twice kt. Vz squared is c squared nu minus nu naught times d nu by nu naught. Okay, so this is how the strength of the line depends on frequency. Okay, so we can actually write this as a line profile phi nu, right? This actually can be written as a line profile, which can be normalized, so is equal to e to the minus nu naught whole squared by delta nu d whole squared divided by square root of pi delta nu d. Right? This is a normalized Gaussian distribution, or a Gaussian profile, line profile, where delta nu d is equal to, we can just read off, right? It's just nu naught by c times twice kbt by m. So here m is the mass of the atoms which are moving. Basically, this is the mass of the radiating species. So basically, the line profile now, right? This line profile is a Gaussian line profile. Let me actually draw it on the same graph, right? So this will be like this, these, this is Gaussian, falls off quickly away from the core. Right, so my drawing is a little funny. I mean the area, of course, under the two curves should be the same, right? Because these are both normalized line profiles. Okay, and typically, right, so delta nu d by nu naught is like twice kt by m by c, right, which is equal to V thermal by C, which is much less than 1. So this is pretty narrow. Delta nu by nu naught is of order V thermal by C, which is much less than 1. Okay. What about the cross section? So line center cross section. So we can actually ignore stimulated emission, and what we get is sigma nu naught, the cross section, the emission or absorption cross section at the center of the line, basically here. What is it? This is equal to B12 h nu by 4 pi times pi nu naught, and we are calculating this is at the line center. And right, so basically this is, we can actually, these are all related. This is cross section. This is, we are ignoring stimulated emission. So that's why we don't have minus B21 term. We just have true, we just have absorption. So you have 1 and 2, and you are absorbing, and then electron going to higher state. So cross section is always proportional to these Einstein's A and B's and the line profile. So what is the line profile at the line center? This is nothing but 1 by. So if we evaluate this pi nu naught, this is 1 by square root of pi delta nu d times h nu naught by 4 pi times B12, right? So, and we know that delta nu d is nothing but 1 by square root of pi nu naught V thermal by C. Times h nu naught by 4 pi B12. So what it means is that if a larger cross section for a narrower cross section at line center for a narrower line, right? So because if delta nu d is smaller, your sigma is bigger. So you have a sharper line has a higher cross section for absorption, and we can actually write this as sigma nu naught is equal to pi e squared by mc. This is like a standard form, f12 1 by delta nu d square root of pi. Same thing written in terms of something called an oscillator strength, which is proportional to the Einstein's A and B coefficients, and it sort of quantifies the strength of these transition between 1 and 2. This is called oscillator strength. And numerically, this is equal to 1.2 times 10 to the minus 14 centimeter squared lambda naught. A by square root of t, A by t f12. So let's see where these are coming from. Square root of t by A is just the thermal velocity, right? This gives rise to this. This nu naught so C by nu naught is nothing but lambda. That's just this. And then there are these are the other terms. So this is this is proton, this is the mass of emitter in terms of proton mass. Thermal broadening, this is thermal Doppler broadening. But you can have an additional process if you have, in addition to just the thermal motion of electrons, if you have turbulent motions as well, then the turbulent motions and the thermal motions add to give Doppler effect, right? So you have delta nu d. In that case, the width of line profile is equal to nu naught by c times twice kT by m, mass of the atom, plus z squared. And this z is like, turbulent speed. You have thermal motion and then you have like random motion, not because of associated with temperature, but just because of fluid motion. So the two motions add in quadrature. This is due to thermal motion and this is due to turbulent motion. So by measuring the line, so measuring line profile can actually give you, can give us a hint about turbulent velocities in the medium. Okay. So this is just a Doppler broadening. We talked about natural broadening. Now, we have both, and an atom will not only have Doppler broadening, but also natural broadening, and the two have to be combined together. And this is what we'll actually do in the next class. Okay. So I'm going to end now. Any questions? So in the next class, we'll talk about how the natural line profile and the turbulent motion of and the thermal and turbulent motion of the particles together give rise to the observed line profile. Okay. Any last questions?
Sir, about exams, when are we having it?